Yeah, but we're starting in 10.1 to get up to 10.7. I need to remind you of where we've been to see where we're going. So a sequence is a list of numbers. Now, technically, we're working with infinite sequences, but I leave off the infinite part. But when I say sequences, we should all be thinking infinite. And when we think infinite, what do we think?
Oh, we think series?
We think limit, right? Infinity isn't a number unless you're programming in JavaScript, I just heard, which is a whole other story. Anybody here program? No? You do a little bit? Pete was telling me in the Java number system, infinity and negative infinity are actually treated as numbers, which is, physicists think it is, so maybe physicists had their hands in JavaScript, I don't know. Okay, anyway, it involves limits. So if I give you a particular sequence like a sub n equals 2 to the n over n factorial, which is a beautiful sequence, then what should we do with that? Before we do take the limit, what should we do? We should list out a few terms. Yeah, we should list out a few terms. So I would say for this particular sequence, it's excellent to have intuitions that you can't help but shout out, Jeff, but we should definitely mess around a little bit. So first term would be 2 over 1. Second term is going to be 4 over 2. And you could reduce these after or on the fly, whatever you like. Next term is going to be what, 8 over 6. And I'll list one more just for the heck of it, 16 over 24, yeah. Okay. And all those reduce, but that's a whole nother story. And this goes on forever. Now we played with, might have been this exact one a week or two ago, because we took its limit as n increased without bound to the n over n factorial. And what do we believe this is? 0. Yeah, not only does it converges to 0, right? So whenever possible, we state what it converges to. All right, and so I had an argument for why that worked the way it was. And we established in class that factorials beat just about anything they come across. Not everything, but just about everything. All right, so that's limits. Sequences are what? Lists, and they're long, so we take limits. How long are they? Infinitely long. Excellent, beautiful. Okay, so that was section 1, which is a huge part of everything we do. That beats a factorial. Right, because instead of n times n minus 1, this is n times n times n. And how many n's are there? N. There's n of them.
I have never, that's really weird to think of. Nice.
It was in the homework. Yeah, the homework said it was either the limit as n went to infinity. I think it might have been n factorial over n to the n. And they gave you a hint on how to do it in the homework.
I don't remember either, but I'm pretty sure it was there and it was really scary.
I was sure I put it in the homework.
But I made sure that I had all of my homework done before I decided to get it.
Okay. And it could have been a dream, but I have a strong recollection of doing that one in class, maybe on the same day as this one. Yes, oh yeah. You can. Okay, all right, back together. Okay, that was exciting. Zach asked if you can mix factorials and powers, and yes, you could. So you could have some strange creature like n to the n factorial. Yeah. Or change the order of operations, and you could try n to the n factorial. Different order of operations. So one question is, which one's bigger, the blue one or the red one? Because they're not the same. I think you're right. I think it's probably the red one too, but I'd have to play around to see. But okay, anyway. All right, so getting a good grasp of sequences, and the main thing we need to be good at with sequences is what? Limits. Limits. We need to be good at limits. Okay. Yeah, that's okay. Maybe my questions aren't very good. That's right. Series comes next. Now series is when we take one of those lists and we try to add them up, like the sum as n goes from 1 to infinity up to the n over n factorial. Now this is more complicated, because not only do I have a list of numbers, but I'm adding them, and I'm adding them forever. When we do this, we have partial sums. So this sucker right here might be called S if it converges. Do we have an intuition on whether this converges? You think it does converge? No, we did the sequence, which is different. Yeah. So the sequence goes to, because, whoa, hold on. I'll let you do your epiphany in a second. We know the terms go to 0. Does that mean the sum will converge? No, it does not. It's a candidate for convergence, yes. Yeah. So the fact that the limit, forgetting the sum for a moment, but the fact that the limit of the things I'm adding happens to go to 0 only makes it a candidate for conversion. Candidates. There we go. That's called, it's a lot, in a lot of books it's called the nth term test. It should be called the divergence test, because the test only gives us conclusive results on divergence, not on convergence. So it's a candidate for convergence. It's a necessary condition to converge, but it's not sufficient. Okay, it is necessary, but it's not good enough reason that'll converge. We have to do something else. So what does that something else entail? Well, ratio test is what I'm going to go for in a minute, but just I want to remind you that we accumulated a heck of a lot of tools. So let me bring some of those tools up here. And I gave you that cheat sheet, which unfortunately you can't use on the test. Unless you put it in your calculator. I know, there's always the put anything you want in your calculator option. I know, but I trust you guys implicitly. Okay, focus. Okay, you guys get 1 second and you just like, whew, you're worse than me. I thought I was, had issues with focus. Jeff makes me look really focused. All right, so I gave you this cheat sheet. It's a summary of all the different tests that we've done. It's pretty similar to the way the book presents them. I've got some comments here about them when I can. One of the hardest things to deal with, in my opinion, are remainders, and they're just going to remain hard, and that's it, okay? We're going to continue to work with the remainders and the new stuff we're going to do. I think the most powerful test is the ratio test. The root test is equally powerful. I love the limit comparison test. That's one of my favorite ones too. Integral test is pretty cool because I can bound the remainder with it. So there's a lot of great stuff here. But you got to know this stuff, which means you have to practice a lot to know it. And you've got to write stuff down. What's the problem with the homework, Jeff? It doesn't require you to write stuff down. They give you the statement for you. You can kind of guess at it, right? That's a problem. And so you got to practice writing stuff down. So my hope is that before you took the test, you practiced writing stuff down. We've been having a hard time finding time to get together. Oh. Oh, you want me to put a special thing up? Well, I gave you the practice test. Isn't that special enough? Maybe. I didn't get your test yet. It's possible it got lost. All right. Yeah. See, I don't want to do a. Well, I guess I could do a review, a test. Well, that was what that I gave you one, right? Okay, so you want like another version of the sample test? Is that what you're telling me here? Right. There's, I could make a test with the online system. Is that what you want me to do? Use the online homework stuff to make a practice test? Yeah, I can do that. I might already have one written, but nobody asked, so I didn't put it up. Sorry. Bad me. Yeah, the main reason I think I avoided doing that is the online stuff does not require you to write anything down. Okay, I don't have one pre-made, but I can make one. I'll do it after class. Please remind me before you go away, okay? Yeah. That's her idea, yeah. Okay. So where are we? Okay, all these tests right here. So which one are we going to apply to the problem at hand? We're going to do the ratio test on that. Yeah, factorials pretty much require the ratio test. So the ratio test, my version of it is the limit as n increases forever. I like to throw the absolute value in there, kind of a reminder of the L absolute or conditional convergence idea. When you're doing a series, the default reaction should be it's absolutely or conditional convergence. That's okay. You can pretty much tell by looking for most of them. Yeah. Okay. So then it's a sub n plus 1. I like to do times the reciprocal of 1 or times the reciprocal of a sub n. Ooh. Okay. Yeah. So yeah. So if a sequence is always positive in a convergence, it is absolutely convergent. When there's negative involves. And the cool thing about absolute convergence, although the alternating series test requires strictly alternating, absolute convergence has nothing to do with strict alternation. You just strip the signs. If it converges, everything's good. It's pretty cool. Okay, so we're going to apply this here. So we get the limit as n increases. And oftentimes I won't write the limit until I've cleaned up this mess, right? I'll do that algebra first, but I'm just going to write it all out. So let's see, we have a 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. And then I reevaluate, do I need those absolute values anymore? And I do not, right? Everything's positive. And then a whole bunch of shit cancels. 2 to the n goes into 2 to the n plus 1, leaving a 2. Although it's really nice to just put lines through the factorial stuff, since they're new to us, it's a good idea not to, and just remind ourselves, what does n plus 1 factorial mean? Okay. Because if it was like 2n minus 1 factorial, then everything changes. And we'll do one of those today. Okay. Now that I've reminded myself what these factorials mean, I can clearly see that a whole bunch of stuff cancels. And isn't it gratifying to just wipe all that stuff out like that? Feels good. All right. What's left? What is not canceled? 2 over n plus 1. And that goes to 0. Right, Courtney? Jeff? You guys are focused here? Okay, I love n plus 1. All right, so sequences. Do we need crazy tests for sequences? We just need to know how to do limits. Okay, when we start adding them up, which is called a series, do we need crazy tests? Yes, they're very complicated. All right. Ready for something new?
I believe that I am.
Okay. And in this new stuff, we'll get to revisit the old stuff for the next week and a half. I think it'll take to finish this. I could be wrong. It could be 2 weeks. So, reminder, what kind of series is that?
Oh, that's a geometric.
Geometric. Is it convergent or divergent? This is divergent. Okay. Divergent geometric. All right. What kind of series is that? That's also geometric. but it's convergent. Beautiful. Convergent geometric. So you get a good, it sounds like you guys could recognize any geometric series, right? So a geometric series is something that looks like this. You're adding stuff up, and the stuff you're adding has a base, let's call the base x for a minute, and a power. That's a geometric series. What letter does the book usually use for the base? Pop quiz, see if somebody can win this. What is it? R, just R. A is usually the first term, and R is the bottom, the base. Okay, I'm throwing an X in. Is that okay? Sure. What conditions does X give us convergence? Converge if X is less than 1 or greater than -1. Yeah, turns out if it's between -1 and 1, you converge. And it is divergent if X is outside of that. So another way to say outside of that would be the absolute value of X is greater than 1. Another way to say the convergent part, come on, red, there we go, is that the absolute value of X is less than 1. And let's see, the divergent should be or equal to. Because if you add up a bunch of 1s forever, you have a big number, and a bigger number, and a bigger number. All right, I'm going to write this out for a minute. That would be, let's see, since I started at 1, I'm starting with x plus x squared plus x cubed, and I'm getting kind of tired, so I'm going to stop there for a minute. What is that? That is a polynomial. Oh, but we could keep going, right? We could put a 4th power. And why the hell not just go on forever? Okay, it does, but I could abbreviate that writing with notation we all agree upon. X goes from 1 to infinity of x to the n. That is an infinitely long polynomial. You don't like it? Yeah. Infinitely long polynomial. Do infinitely long polynomials actually exist? Are they useful? Turns out they are. So people for a while, people were like, well, that's ridiculous. How can you have an infinitely long polynomial? It's nonsense. But a few hundred years ago, or maybe even longer, a few people said, well, actually you can, and they can be useful. And a geometric series is an infinitely long polynomial as long as you pick the right x values. If you pick x values here that are between 1 and -1, you're going to get an answer out of this. So if I say f of x equals this, right, then we can figure out what is f of 1/2. Right, let's do it. F of 1/2 is the sum as n goes from 1 to infinity of 1/2 to the n. What's that look like? Well, it's a half plus a quarter plus an eighth, blah, blah, blah. But does anybody remember that we actually have a formula for determining what the summation value is? A being, what is A? The first term, so the 1/2, yeah, divided by 1 minus r, which is 1 minus 1/2, or 1 minus x in this case. Okay, so 1 minus 1/2 is a half. A is the first term.
We start at 1.
A is always the first term. Okay. Yeah, no, so you got to be careful. In some of the formulas, they give you a formula in such a way that when n is starting at 0. To not worry about that, A is always the first term, R is the ratio of any two terms next to each other. I got no number in front, though.
I'm not of the equal sign, but in front of the 1/2.
What's in front of the 1/2? That's a problem. So who's right, the book or me? Well, the problem is the book started off with 0, n equals 0. And if you start off n equals 0, it's going to look different. Okay? Because check it out. If I factor out a 1/2 here, then I'm going to get 1/2 times 1 plus 1/2 plus 1/4, yada, yada, yada. And then there's your A right there. Need help there? Got it. Yeah, so I'm pretty sure that's what this is going to come out to. How could we check? Like, my claim is that f of 1/2 is 1 here, according to that formula. How could I check if that's true? I might have just made that stuff up.
Plug it in.
To what? Plug it in. Like a calculator or a computer? Excellent idea. I mean, we have a formula we use, but between Courtney and I, it's questionable whether we're right. One of us is wrong. Or maybe both of us, right? So whip out some technology. Do you have a check my answer button on the test? No. Do you have me to ask questions to at the test? No. But you have your calculator. Yeah. I might need to give you my telephone number in case like Courtney's problem comes up again. You have a time limit and you can't use GeoGebra. That was not cool. She didn't know.
It doesn't really matter though, because I don't
Yeah.
know how to use GeoGebra. That
Okay.
one. I was just try
Okay.
the test and I figured it out.
Roll that stuff down.
I
A lot of good that does you.
So in GeoGebra, I could just go, if I just want to see a list of numbers, I could use the sum sequence feature, like on the calculator. My expression is what again? Let's see, it's just 1/2 to the n, right? That's what I decided to do. Parentheses 1/2, close parentheses, raised to the n. My variable is n. I'm starting at 1. Super careful of starting value. And let's go 100 terms. I wonder if it, like, maybe if I pick like an X, if that'll get grayed out. I don't know. Good question. Somebody writing the software thought it was significant to do so with n. And GeoGebra adds up the first several terms. Oops, what did I do? I typed something wrong. GeoGebra wants X to be a variable, apparently. At least this version, so I should use n and apply and OK. And to the best of GeoGebra's rounding ability, the answer is 1 after only 100 terms. Okay, so I think my formula was OK. Right, so be careful with your formulas. Should you always check yourself with a little numerical check? Absolutely. It's a good idea. Don't just rely on formulas you think you know. Rounding, let's go 5 or 10 decimal places. Let's go 15 decimal places. Yeah, even at 15 decimal places, GeoGebra thinks it's 1. Let's blow up the font. There we go. Okay, we'll come back to GeoGebra. All right, so what I have here is an infinitely long polynomial. And in math, infinitely long polynomials are usually referred to as power series. Series in math usually means infinite series, right? Power, I have a bunch of powers of some variable like x. Okay, there's lots of different power series out there. Okay, so here's another one. I could have 1 plus x plus 2x squared plus 3x cubed plus 4x to the 4th. You see a pattern?
Plus 5x to the 5th.
Plus 5x to the 5th. Can you write that in summation notation for me?
N starts at 0.
If you wish, but it doesn't have to. Okay? No, doesn't have to. I'll show you. Anyway, if it starts with 0, what am I going to write down next, Jeff? X to the n? Okay, times what? Times n? Okay, and according to this, what's the first term? Hmm.
Why not n plus 1 times x?
Ooh, can I make it a derivative?
N plus 1 times x to the n.
If I put a plus 1 there, then my first term will be a 1. The second term will be 1 plus 1, which is 2 times x. That doesn't work either. Okay. Huh. It does look like a bunch of derivatives, except for which term? Which term is giving us trouble here? The front one is giving us trouble. So these guys seem to behave in a certain fashion. So maybe this is 1 plus the sum as n goes from 1 to infinity of n times x to the n. How about that? Here's the bottom line. There's not necessarily one formula that satisfies any situation. Sometimes we got to split it up a little bit. Okay. When we write summations, should we be careful about whether they really work? That's not right. This isn't right? Okay. Okay, so if n equals 1, so I got this one out front here, right? So that guy just comes down. Then I got plus. If n is 1, I got 1 times x to the first. No, this is 1, x to the first is just x. 1 times x is, that's still x. You all right? Plus, are we okay now? It works. Okay. You see here? All right. So this part of the series, that's no problem. I can handle 1. This part of the series is the problem. So we're going to analyze that. No, it's separate. Order of operations. Yeah. We got to do this stuff before we can add the 1. Yeah. Okay. Add 1 each term. Okay. I see what you're saying. To do what you were thinking, I would have to write it like this: the sum of 1 plus n times x to the n. That would be a problem. Okay, that's what you're thinking. That's not what I wrote. All right, good. We're getting better at notation. Did you write any of that down? Oh, good start. Okay, so now we're going to finish analyzing this one. N equals 1 to infinity, n times x to the n. So it's a series, right? Okay. X could be a lot of possible numbers. I need to narrow down which numbers are good and which numbers are not good. We might guess, based on the previous series we just looked at, power series, what might we guess here? Between what x values might be good here? Like, is x equals 1 okay here? So if x equals 1, that would give me the sum as n equals 1 to infinity of n times 1 to the n. Okay, 1 to the n is what? That's just going to be 1. So this is the sum as n goes from 1 to infinity of n. And what do you tell me about that? It diverges rapidly, right? That's 1 plus 2 plus 3 plus 4. Okay, so this is divergent. Yes. The limit as n increases of n is infinite, so this passes the divergence test, which means it diverges. Okay. So if this was on the test, I would expect to see diverges by what test? Let's not call it the nth term test. What's a better name for it? The divergence test. Thank you. You're messing with me. Yeah. Did you write that down a lot, Zach? Okay. Ratio test wouldn't apply here. If you applied the ratio test, you'd get 1. Okay. Okay, we'll see. Well, you're in good luck, because so far I have not received your test. Maybe you got lucky and they lost it. Okay, so what if x equals, somebody guess at an x value that might work here?
17.
Well, excellent, 17. All right, I like that number. It is a good number. Oh, crazy 7 there. Okay, we'll just leave it like that. So that'd be the sum as n goes from 1 to infinity of n times 17 to the n. Yeah, that's a variant on a geometric series.
It's more than one, so.
What test would we use to prove that this diverges?
Oh, then we
The,
use
the divergence, oh, we could just use the, well, no, it's not a geometric series. We could, because the n. We could compare it to a geometric series, or we could just use the divergence test. Yeah, what's the limit as n increases of n times 17 to the n?
A lot.
A lot.
17 a lot.
17 a lot, yeah. It's infinite.
17 times
So again,
a lot.
diverges again by divergence test.
1,734. 1,700.
Oh. Yeah, so like Zach said, a proper fraction, right? So you said, what if we let x equal 1/5? Zach said, or fifths. That, yeah, okay. If either of these were the base, we'd be okay. I think 5, right? Okay. So if we used either of those, we might be okay because those are related to convergent geometric series. What test would we really use to prove either one of them, though? Let's pick on this one because it's the first one because it's easier to write. What test? The integral test? I would not want to integrate that, but you could. You'd have to do integration by parts on it, which is okay. It's fun. I mean, come on. Who doesn't like to do that on a Friday night with a beer? No, you can only apply L'Hopital's rule to limits, and we're not at a limit yet, okay? This will fail the divergence test in that the limit of the terms goes to 0, which doesn't tell us anything. We could root test it, we could ratio test it, we could do a comparison on it, or a limit comparison on it. Okay, we got a whole bunch of options here. Okay? Well, if you do the divergence test, you get nothing. Yeah, because what you're going to find is the limit as n goes to infinity, that's an infinity, of n times 1/5 to the n, that goes to 0. And the divergence test tells you nothing. Yeah, it just makes it, it's still a candidate for convergence, but it might diverge. Okay. So I'm going to use the ratio test because that's my favorite. So the ratio test says to take the limit as n increases, whoa, of, and I usually do absolute value, but that curved, so we're going to go with it. So let's see, what do we have? We have n plus 1 times 1/5 to the n plus 1 over n, oops, bad notation, you got to have parentheses, times 1/5 to the n. Cleaning that up, what do we get? What happens to the 1/5 to the n type things?
Oh,
It just becomes 1/5 on top, which multiplying by a fraction is the same as dividing by its reciprocal. So that rewrites to the limit as n increases to n plus 1 over 5n. And that goes to 1/5. Is 1/5 a nice number to see if we're hoping for convergence? Yes, because it's less than 1. Okay, so this implies convergence by the ratio test. Now, isn't it true that we could have used the same test with Zach's number? Yeah, same test would work with Zach's number. If the number was 1/7, we'd still use this test. If the number was 0.9, we would still use this test. So why bother picking x values when we can just apply it to the series by itself? So we're going to take x is just, it is, and x is just some number, so let's just apply the ratio test to what we see. Okay, so we're going to apply the ratio test leaving x alone. We're not going to call x 1/5 or 1,734 over 1,735. We're just going to call it x. So we're going to take the limit as n increases. Absolute value's got to go there this time because x can be any number. N plus 1. Well, we're going to find it. That's an X. Okay. That's what the ratio test looks like according to this problem. Write this down, Jeff. Please. You'll make me happy. All right. Does anything clean up a little bit here, Anna?
Well,
Anna. You're loud. She's quiet. I want to hear from Anna for once. Tell me, what do you think, Anna? Yeah, the X's and N's, shit happens, right? So X to the N plus 1 divided by X to the N is equal to, yep, X. Now at first, the N plus 1 over N, there's not much I can do with. I'm just going to rewrite it. Now, what is N ever negative here? N, the counter. No, N's my counter, right? So it doesn't even need the absolute values. So I'm just going to separate this a little bit. Because what I have is I have N plus 1 over N. It's always positive. But X, I don't know, so it has to stay in the absolute value. Now, even better, does X have any N's in it? There's no more N's with that. So I can rewrite this yet again. I can pull the absolute value of X out of the limit, and then I just have to consider what the heck is the limit as N increases of N over N plus 1 over N. That goes to what? That's 1. Oh yeah, we could have done that too. Yeah. Yeah. The only thing left is the absolute value of X. True. So what we found is our limit as N increased of A sub N plus 1 over A sub N. We found that that was equal to the absolute value of X. Now, what does the ratio test say about the result of that limit? What must be true for convergence? Yeah, it says this has to be less than 1 for convergence. Have we just identified a whole bunch of X values for which this seems to converge? Yeah. An infinite amount. Yeah. So we have convergence for any X value bigger than -1, but smaller than 1. That's a good point. Okay. So generally, we're going to apply the ratio test to these, and the ratio test tells us what happens inside some radius. Okay. So here, the center of this interval is 0. Would you agree with that? Center is 0. And then the distance out from that center is 1. Right? So this is what's called, 1 is called the radius of convergence. Okay. Now, what does it mean to have all these X values it converges at? Well, it means that if we pick one of those and plug it in, we can get an answer out. Sort of. Question, Courtney? The radius of convergence. Okay, so if I draw a number line here, right in the middle is 0, out to this side is 1, out to this side is -1. 0 is the center of the interval, true?
yeah, I got you.
Okay. Yeah, so from the center of the interval, I can go out 1 to the right or 1 to the left. So we say this is an interval of radius 1, distance from the center to the edge. Okay. So what the ratio test is going to do is going to give us an interval centered somewhere. We can say the radius is blah blah blah. In this case, it's 1. What does the ratio test tell us about at 1? It tells us nothing. It is inconclusive. That means we have to use other tests to check out the endpoints. Okay. Ratio test only tells us in between the -1 and 1 stuff. We have to look outside with other tests. So let's just make a little note. Running out of room. We'll go to a new page. We have to check the endpoints with other tests. All right. So before I do that, I'm just going to bring up GeoGebra and have it graph. Now, GeoGebra can't graph infinitely many terms, but it can graph a lot. Okay. So what I can do is I can do a partial sum on this power series. So where's GeoGebra? There she is. Okay. So I am going to throw x's and n's in here. So I'm going to sum a sequence. And my sequence, I'll do the one we just had. It's going to be n times x raised to the n. Variable of summation is n, starting at 1, and I don't know, what should we go, 50 terms? I think GeoGebra can probably handle that. And GeoGebra is going to see the x's, and it's going to make it a function. Ooh, check this function out. All right, so let's resize it a little bit. Now I'm just going to graph a couple things. If I graph, what were our boundaries on x values here? 1 and -1, right? Yeah, so if I graph x equals -1, it's that vertical line. X equals 1 is that vertical line. Let's change their look and feel a little bit. Yeah, it just took off like a madman or woman, something like that. Let's see, color, we'll make the boundaries red and dotted. How about that? And fat. And we'll do the same for the other side. Fat, dotted, red, line. Okay, and so let's just change the scale here too. We'll zoom in between -1 and 1. Do I got it? Oops, I'm a little too far maybe. Okay, there it is. And then we'll just come down a little with this. So it behaves kind of nice near the origin, but then it takes off on either side. It becomes divergent on either side. Now, the more terms we add, my guess is this side's going to start hugging into that vertical line there. It's going to start getting closer. I could double check by seeing if GeoGebra can handle 100 terms. And it hugged in just a wee tiny little bit. This side didn't change too much, it didn't seem. Okay, so right now we're looking at the 100th partial sum of this power series. Okay. Pretty cool. And it looks really well behaved near the origin. And then away from the origin, it's starting to do some really funky stuff here as it just goes woof, skyrockets. So why do I care that it takes off or that it behaves nice in the origin or any of it? Okay, so that's a good question. So think of a number like pi. Pi has a lot of decimal places, right? And they occur pretty much randomly to the best of our knowledge, and it's very hard to compute them. How do people actually compute the next digit of pi? Like, I know 5 of them, 3.14159, and then I go a little brain dead. What's the next one? How do I calculate it? Well, I push a button on my calculator. How the hell does the calculator find the next number and the next number and the next number? You know a division algorithm for finding digits of pi? Long division applies to some stuff, but not all. Like, I can figure out repeating decimal with long division, but I can't easily use long division directly to, say, find continued decimal points for like the square root of 2 or pi or e. I need some other math. This is one of those other kinds of math, at least for figuring out the value of pi, the value of e. The other thing, there are a lot of functions out there in the world. Lots of them. You found many of them. Polynomials, logarithms, exponential functions, rational functions. There's a whole ton of them out there. Turns out there's a lot more that can't be described by using addition, subtraction, multiplication, division, and roots. Trig functions are some examples of that. Trig functions don't use addition, subtraction, multiplication. They use these crazy ratios and triangles and circles. It turns out adding up powers of x forever and ever with special coefficients give you whole new functions that we didn't know existed otherwise. And without them, we couldn't describe how electricity moves in certain ways. We couldn't describe the way a drum head vibrates, where we hear radio waves, and all kinds of other things like that. So there's an area of math called differential equations, and differential equation solves problems where things change regularly. Okay? Like, it helps me find an equation to the temperature of a body as it cools off, whether it's a cup of body or a dead thing. Okay. And there are some problems in differential equations, like how things change. Like if I were to whack my pen on the table, I can feel it vibrate for a moment, and the vibration dissipates. Okay, so I can model that with mathematics, and there's some of those things I cannot model without these infinitely long polynomials. Turns out it's impossible. Can we add infinitely many terms? No, we can't technically, but we have techniques for saying how far out is far enough that I can build a bridge with this knowledge, because I can estimate remainders, like you were worried about remainders before. Does that help a little bit?
I don't understand why you care why it acts so nice.
Oh, if it doesn't act nice, I can't use it. If I can't say when this is applicable and when it's not, it's worthless. Right? So with the tests, I'm saying you can only use this list of terms if you stay between -1 and 1, but don't get too close to the edge if you didn't add enough pieces up. Because according to the theory, I can get to the very edge of -1. Now, you can get as close as you want for ever and ever. The problem is if I don't add enough terms, I'm going to be in trouble. With me? So the remainder theorems are going to help us figure out how many terms I have to add up before I have to say, hey, you better stop using this. Because after about 0.9-ish, -0.9-ish, this thing is useless. That's why they're important. Yeah. Yeah. So at first we're starting off with sequences and stuff that we can kind of predict what they do, because there's a lot of other sequences out there that we can't nail down what they do exactly, but we have this general theory that says, hey, you meet these conditions, you're okay. All right. So let's back up a step. Let's take a look at a slightly different function. Let's turn U off, and U off, and U off, and U off, and U off. Come on, turn off. There you go. All right, we had another sum we did earlier, the basic geometric one. I'd like you to try this on your TIs too. What I want you to do is on your TIs, if you don't have GeoGebra up, I want you to graph the 10th partial sum, of the sum as n goes from 1 to infinity of x to, I guess I didn't need parentheses there, x to the n minus 1. All right, what does that look like? Okay, good question. You pick another letter, like instead of n, you could use anything else. All right, I guess I better do it with you. All right, so if I want to graph it, it's got to go in the y equals menu. So in the y equals menu, I want to do a sum of a sequence. So then I'm going to have to go to the list menu there, bring up sum, which is under math. Oh, or we could use that fancy button, I bet. I forgot about the fancy button. Alpha window, number 2. I keep forgetting that exists. Okay. Yours won't let it do it there? I can, if I update your operating system, I bet it'll do it. I could do that sometime for you. Okay, so without the fancy thing, you're going to have to do what I was just going to do. You're going to have to go to list, math, option 5, and then sequence. You can't have x, so x cannot be your summation variable, right? That's got to be a different letter. I would use A, it's easy to find. Yep, doesn't matter what you call it, yeah. Okay.
That's what I was asking, but I guess it doesn't matter.
It's gonna start it at 1, yeah.
How many?
Okay, hey, I'm getting there. So my expression, let me clear that mess out. My expression is going to be x as the base, raised to the power parentheses, and then I'm going to use a minus 1. My variable is a, because it's the counter that it wants. Starting at 1, go to 10, step by 1, paste. The calculator is going to struggle with this a little bit. So then I'm going to do zoom 6 for a standard viewing screen. Oops, I forgot I was graphing other stuff. I was graphing histograms in my other class. I got to turn that off. Let me fin it, calculator. Okay, let me do this in GeoGebra. It's a little quicker. Okay. Oh, you can use your fancy button too, can't you?
Not in the.
Oh, it wouldn't let you use it there? Oh. Yeah, so I'll write down the command here. I was about to do that. So this would be Y. Does let's see, does the calculator spell out sequence or just do SEQ? SEQ, okay. GeoGebra spells it out. It's a little different. Okay, some sequence of x raised to the, I used a minus 1, comma a, comma 1, comma 10, and that should be sufficient to get the first 10 terms. All right, so that's the calculator terminology there, or syntax. GeoGebra, some sequence, and pretty similar. Here I'll just do x raised parentheses. I can use n here. Variables n starting at 1, ending at 10. Enter. All right, I get that graph right there. Now, was this valid for all real numbers? Anybody remember? It's between -1 and 1, so I'm going to put those boundaries back in. Okay, so this particular function is only applicable between -1 and 1. Now here, we only added 10 terms. Now don't dare give the calculator 100. It will freeze up. But I can probably give GeoGebra 100 terms. Now watch how my graph changes. It might not be instantly. Oh, mine, wow, that happened pretty damn fast. Okay, so check it out. Here's my function right here. So sometimes, like with a series, you can say what number it converges to. Sometimes with power series, you can determine what function it converges to. Now, are we graphing a power series here? Is this a power series? Yes. Is it a geometric series? It is a geometric series. And don't we know how to tell what number a geometric series converges to? Isn't it always the first number? What's the first number here? X to the 0, which is 1. Yeah, so this is 1 plus x squared plus blah, blah, blah. It's pretty boring to look at. But geometric series says the limit of this is 1 over what? What does geometric series say about the sum? And R is x, so 1 over 1 minus x. That's a function. Graph that function next. Can we always pull off this trick? We can't always pull off this trick, but we can try. All right, so I'm going to colorize. I'm going to make this thing blue. Or a little, that's a nice blue there. Okay, so there's my blue function. So now I'm going to type 1 over parentheses 1 minus x. Close parentheses. Enter. Ooh, look at that. They sit tight. You can't even see the blue one hiding behind there. Let me blow it up. The black line sits right down the middle of the blue line. They look indistinguishable until you get close to the borders. Okay. Is it always that tight? No, it depends on how many terms you added. If you were somehow able to add all infinitely many, they would be a perfect match for each other. But we can't add all of them. We can only add so many. Okay, and we can do some error analysis later that tells us when, with the terms we added, we start to diverge too much from what it should be, infinitely. Okay, and this is going to take a couple weeks to get used to, but we're off to a good start. Let's see. Does it look like it might converge at the endpoints? What are my endpoints here? -1 and 1, 1. The ratio test doesn't tell us anything about the endpoints. You have to use other tests to check that out. Okay, so we'll have to do that. Pretty neat. All right, so I'm going to do a little play here, and then we'll test some endpoints. And generally, that's the procedure. We get a power series, we run the ratio test, most likely, maybe the root test, then we check the endpoints. That's the routine. Okay. I like to plot a few terms to see what it looks like. If I know what it converges to, I like to plot them together to see if I'm in the ballpark. But with the regular series, were we able to say what it converged to a lot, or were we just able to say it was convergent? We were just able to say it was convergent. And that's going to happen with power series. We're going to develop all these power series, and we're going to say that they're convergent or not, but we don't know necessarily what they converge to. It could be they converge to something totally unique humanity has never seen before. It's true. It happened. Oh, lots of times, yes. People discovered these series, and you're like, oh my God, nobody in the world has ever seen this before except me. I'm going to show everybody. I'm going to tattoo it on my back. It's going to be the greatest thing ever. Yes. Yes, some sequences create new numbers that nobody ever knew of before. Like pi or e. Somebody had to find those once upon a time, right? Oh, that's not the magic test. What was that, Zach? The golden ratio can be found using series and a lot of other methods, yeah. Like, you ever hear of the Fibonacci sequence? Yeah, so if you take the ratio of consecutive terms of the Fibonacci sequence, it gets closer and closer to the golden ratio, which is pretty cool. The golden ratio is, I think it's 1 minus, no, square root of 5 minus 1 all over 2. And geometrically, it has a lot of significance. One significance is it's a shape of a rectangle, like length divided by width, that is very pleasing to us. So if you look throughout humanity at nice architecture, you'll find the golden ratio in it often. And it comes up in a lot of other places, like Zach was saying, the pattern in certain seeds and flowers as they kind of cycle around does what's called Fibonacci number. There's one, then there's another one, then there's a pack of 2, then there's a pack of 3, then there's a pack of 5. And if you take ratios of those numbers, as you move through that sequence, you approach that magic number of the golden ratio. Yeah. Anyway, new sequence. I'm gonna screw with this just a little bit. So we have the sum as n equals 1. A lot of times they start off with 0, so I'm just going to mess with you. I'm going to start off with 0 this time. And I'm going to put just an x to the n there. That would be 1 plus x squared, blah, blah, blah. Goes on forever. We know this is a geometric series and that it's equal to 1 over 1 minus x if, in absolute value, x is less than 1. All right. In other words, geometrically, I have an interval with 0 at the middle, and I can reach out, and as long as I stay no more than 1 unit away from 0, I'm okay. So inside of this limit, inside of those boundaries, I'm good. So we say this is an interval centered at 0 with radius 1. I'll do some that aren't centered at 0 without radius 1 shortly. Okay, so I'm just going to mess around. I'm going to do a what if here. What if we replace x with negative x? Well, when we replace things, I should be careful and use parentheses. So that would give me the sum as n goes from 0 to infinity of negative 1 to the n, or negative x to the n, sorry. Which, when I plug in 0, negative x to the 0 is still 1, but negative x to the 1 is negative x. What's negative x squared? It's just x squared. What's negative x cubed? Be minus x cubed. So what happens, what am I generating here when I replace x with negative x? I'm generating an alternating series. Oops, I didn't mean to put a negative by the 5 there. What's that? Actually, when you mentioned absolute convergence, since when we were using the ratio test, we put absolute value on stuff, inside that interval of convergence, you're absolutely convergent. It's only at the end points where you could be conditionally convergent or not convergent at all. Okay, but whenever we use the root test and the ratio test, we're using absolute value, and if it turns out to be convergent, it is absolutely convergent in the interval. Okay. Let's check out what happens to the answer in the interval. According to this, the answer should be 1 over 1 minus parentheses negative x, which cleans up a little bit, doesn't it? Yeah, 1 over 1 plus x. And as far as the interval is concerned, what's the absolute value of negative x? It's the same, well, no, it's the same, it's the same thing as the absolute value of x, so it has the same interval of convergence. So the only thing that really changed here is I have an alternating series, and the function that I think this thing converges to appears to be a slightly different function. It's still a rational function, it still has an asymptote, it's just in a different spot. Okay, I'm going to graph that, check it out. And then we'll test the endpoints. All right, so I'm just going to modify what I have here by putting a parentheses around the x and making it negative. There we go. Okay, so this is no longer the function it converges to, it just flip-flopped a little bit. Right, and if we replace x with negative x, we flip-flop stuff from the left to the right, so that is a horizontal flip, right? Ta-da. And so the function it converges to, if I edit this sucker, I just have to switch that sign. Should be, oh shit, what did I do wrong? Oh, there it is. Oh, come here. Sorry, you can't see it because of the window. It's hiding underneath the blue curve. See it coming out there? And if I scroll up, I should see it diverge over here somewhere, maybe. Maybe not. I guess I need to make it a different color. Let's try what? Object, color, yellow, and really fat. And hopefully we will see it. Can you see the yellow kind of peeking out there? Oh, you can't see it over there. I can see it. There's yellow peeking out right there. I guess if I made the blue less severe, it's there. That was a bad color choice. Let's try again. Color, let's make it like, what's that, like chartreuse maybe? Okay, can you see the pink coming out on the edge there? Kinda, sorta, maybe? Okay, sorry, I should have made it even smaller. Anyway, they're really tight. Are they the same? No. So for example, if I ask what is h of like 0.99, and I compare that to what is p of 0.99, they should be a little bit different. Okay, 0.3 versus 0.5, right? So they're starting to diverge over on the edge of the interval, right? And I meant it to be negative on each side. They'll diverge even more. Apply. Oh, get back here. Uh-oh, what did I do? Negative. Okay, so negative on the left side, they're negative 63 versus 99. Okay, so they're diverging a little bit on the edge, or a lot, depending on your point of view. All right. Now, endpoints. We got to check the endpoints. So right now we know that this thing has a interval centered at 0 with a radius of 1. That's the interval of convergence. We need to know what's going on at the endpoints. So we're switching over to this series, the sum as n goes from 0 to infinity of negative x to the n, which I believe I can rewrite as the sum as n goes from 0 to infinity as negative 1 to the n times x to the n. What do you think about that? And the reason I believe I can do that is that I can rewrite negative x as -1 times x and use the distributive property of exponents to separate them. Okay. All right. So this way, at least it looks more like an alternating series to me. Now, it turns out that many power series alternate whether we recognize it or not. And I'll give an example of that later. All right, so what are my endpoints right here? My endpoints are x equals -1 or 1. So I have to plug those in separately and just see what happens. So what if x equals -1? Then that means my new series is the sum as n goes from 0 to infinity of, I'm going to use the second version. I got my -1 to the n, then I have my x to the n, where x is in this case -1. What happens if you take -1 to the n times -1 to the n? You get +1 to the n. And +1 to the n is usually just 1. So that means this series becomes the sum as n goes from 0 to infinity of 1. On a good day, it's 1. Do you ever have bad days where like 2 plus 2 is 5? Or yeah. No, there's no magic I can do to change that. Okay, so that's a lot of 1s. What does this series do? It diverges, right? Yeah, this diverges. So we're diverging on the left endpoint. Any guesses for the right endpoint? It's forever doomed to alternate, yeah. So this is 1 minus 1 plus 1 minus 1. It depends when you stop what the answer is. If I stop there, the answer is 0. Courtney says, I'm going to go 1 farther than you because I can. Now it goes to 1. Then it goes to 0. Then it goes to 1. Then it goes to 0. Then it goes to 1. Does it ever make up its mind and settle on one of those numbers? No. This thing diverges also. Okay? So we have 2 ways to diverge, right? One way of diverging is it explodes. It just gets bigger and bigger and bigger forever. The other way is it doesn't settle down. And this thing bounces back between a sum of 0 and a sum of 1, depending whether you did an even number of terms or an odd number of terms. Okay? So it's divergent. So now what we've done is we've assured ourselves that for this particular series, power series, x to the n, its interval is for sure between -1 and 1. Right? We've nailed the endpoints. It diverges at each endpoint. What's its radius still? Radius is 1. All right, ready to do some more challenging ones? I think we got the basics down. Here we go. How about the sum as n goes from 1 to infinity of n over 2n minus 1 times 2 to the n. Oh, and then I need my x to the n. There we go. All right, so we're getting a little more complicated. This is a power series because I have x to a power. Okay. First few terms, what do they look like? The first term is going to be 1 over 1 times 2 times x. Now here my first term is degree 1. Sometimes the first term could be degree 0, meaning it's just a constant. It all depends. Second one's going to be what? 2 over 3 times 4, x squared. Third term, 3 over 5 times 8, x cubed. Get a feel for what this is doing. Keeps going. Some days I might add a few more terms. Sometimes I might not. So coefficients. These are the coefficients. The coefficients determine whether the power series can converge or not. Okay. Along with the x values we get to work with. It could be a particular power series only converges for one value of x. Could be it diverges for every value of x. Could be it converges for every value of x. Could be it only converges in an interval. And who knows what happens at the endpoint. So all kinds of things can happen. Looking at these coefficients, what's a guess here? Do you think this might have some values of x for which the whole thing is going to converge? Like, could you handle this sequence without the x to the n? Without the x to the n, what does the sequence do? It converges. So chances are we're going to be able to find values of x that more than just one number that it converges with. Okay, so let's try and find them. What test are we going to whip out? Ratio or root? Okay. Now, when we do the ratio test with series, it's the limit as n increases of the absolute value. Okay. So absolute value here, I'm going to get n plus 1 in the top times x to the n plus 1 over, let's see, 2 times n plus 1 is going to be 2n plus 2, then minus 1. All right, when in doubt, write that all down. That's 2 times parentheses n plus 1, close parentheses, then minus 1. And then I have 2 to the n. Okay. So if you're good at simplifying that stuff in your head, great. If this is a test, never simplify in your head. Write it down. Times the reciprocal, which is going to be of the previous term, 2 to the n minus 1, sorry, 2n minus 1 times 2 to the n over n times x to the n. So there's our ratio test. Start cleaning it up. That should be an n plus 1 here in the bottom, right? Yep, you're correct. Good eye for detail. All right, write something down. Writing this down, Zach? Come on, play along. It's more fun. So there's a little bit of cleaning up I can do. It's about all I can cancel. Now I got to pull things back together. I'll pick a different color. Blue. So let's see, there was an n plus 1 times a 2n minus 1, and there was an x on the top. In the bottom, I got a 2n plus 2 times n times 2. Is that what you guys got? 2n plus 1, sorry. 2n plus 1 there. Order of operations, oops, wrong button. Let's see, I got to distribute that 2. So that's going to give me 2n plus 2, then minus 1. Yeah, so it's 2n plus 1. Yeah. So far I have, I keep hitting the wrong button. That. And so now the question is, do I need to do more algebra, or do I think I know what this reduces to? Where? Here?
No, over.
Here? Here?
That one.
It should be 2n plus 1.
Oh, I thought it was 2 times n.
Yeah, oops. I keep hitting that wrong damn button. Okay, so right here you're talking about, let me highlight this part right there. Yeah, so I have to distribute that 2 through the n plus 1. So that's going to give me 2n plus 2, but I still have the minus 1 hanging out. Yeah. Okay. All right, so I'm going to multiply some stuff out. Now, the x, does that have any n's in it? I mean, it's just an x all by itself sitting there. And the n's, they're all positive. So I believe I can rewrite this a little bit. Check this out. Move you over. I can pull the absolute value of x out and then just leave the n's behind because it's just a multiplication. And so what's left behind then is the product of these guys, which I think is what, 2n squared plus n minus 1 over 2n squared plus n. Oh, times 2. 4n squared plus 2n. And that goes to 1/2. Absolutely. So the whole thing goes to, you could say 1/2 times the absolute value of x. Okay. Let's see. The ratio test says we would like that answer to be what? Less than, greater than something? Less than 1 is what the ratio says. Ratio test says if your result is less than 1, then you have convergence. Okay, so I'm going to solve for x here. I'm going to solve this right here for x. To do that, I think I would multiply both sides by 2. So that's going to give me the absolute value of x is less than 2. Now, what does absolute value mean? One interpretation, it means distance from 0. So this says x is some number whose distance from 0 is less than 2. Right? X is some number whose distance from 0 is less than this far away on each side. So I want x's inside of this region. So 2 is what I call what? The radius of convergence. Yeah. What's the center of my interval? 0, correct. Radius is 2. Do I know if this converges at the endpoints yet? I do not. I have to pull out other tests for that. So that's the next step. So we found the center and the radius. We found the center and the radius by using the ratio test to get down to something without a limit in it. Then we use the fact that the ratio test says you will converge if that result is less than 1. And then we turned that into an interval. Courtney, question. You okay? All right, so endpoints.
Actually, I do have a question.
What is it?
So, that converges so long as x is less than 1, right?
No, it converges as long as the result of the limit is less than 1. I have 1/2 times the absolute value of x is less than 1. What the ratio test says, do I have the original thing written? No. Let's get a new. Right, but when I cleaned up the interval, I came to the conclusion that x has to be between -2 and 2. So if x were 5, I wouldn't have convergence because x is not in this interval. I am. I'm saying if x is any number greater than -2 but less than 2, the original sum, the original power series is a convergent power series. That means that at any of those x values, like if you pick x equals 1.5 and plug it into that original formula, it's a convergent series. If you plug in negative 1.9999999, it's a convergent power series. Okay? All right? So the next thing we have to do is, well, we have to ask the question, well, what's happening at -2 and at 2? Because if I try to plug in 2 or -2 into this, I get a ratio of 1. What's half of the absolute value of -2? 1, and the ratio test is inconclusive there. Yeah, so now we got to test the endpoints. All right, so my original series was the sum as n equals 1 to infinity of n over, was it 2n minus 1 times 2 to the n times x to the n. And instead of putting an x there, I'm going to plug in one of the endpoints. Does it matter which one you pick? Not really. Depends on the series. So either we have to test x equals -2 or x equals 2. Can't do them both at the same time. Let's do 2 first. Excellent choice. Okay. 2, hey, check it out. If we do that, we have 2 to the n divided by 2 to the n.
Get out of there, 2 to the n.
It's gone. All right. So now I have the sum as n equals 1 to infinity of n over 2n minus 1. What test should we use to analyze this red sucker?
What's the question?
No.
Comparison.
Can't cancel the n's.
Take the limit.
Oh, take the limit. Let's take the limit of this. What happens if you take the limit of the term, forget about the sum for a minute?
It's just 1/2. It's 1/2.
Why is that important that it's 1/2?
1/2. And the other thing was 1/2 up there.
No, it's not 0. That's what's significant. Oh,
That's just because the 1/2 up there was.
not related. We got lucky.
We just did.
Yeah. It turns out those, yeah, sorry, bad call on my part. Those two ideas are, that there was a 1/2 from the ratio test and that there's a 1/2 here are totally unrelated. Sorry, there's no connection there. What's significant here is that this is not 0. What does it mean if the limit of the sequence is not 0? The sum diverges. This is the divergence test. So this means the sum diverges by the divergence test. Okay, so on the right endpoint, it fails. Failure. What about on the left endpoint? So we're going to let x equal -2, sum from 1 to infinity. All right. What? What's Zach right about? I didn't hear him. What's true about those guys together? What's -2 to the n divided by 2 to the n? -1 to the n. So this is an alternating series. So this becomes, you can't pull it outside of the, you can't pull it out of the sum, you're right. But I could say it's -1, I can pull the -1 there. So this is an alternating series. Alternating series requires 3 conditions to be met for convergence. Condition number 1 is that it's strictly alternating. Right? If it's strictly alternating, the stuff that doesn't alternate has to be positive. Is that true here? Yeah.
It is positive.
Okay, so that's a check. Step 2.
N is greater than n plus 1. Well, U is greater than.
Step 2 says, is what you're facing non-increasing? Right. So that means if I replace n plus 1s in there, so n plus 1 over, if I replace an n plus 1 on the bottom, it's going to become 2n plus 1. Remember our algebra earlier? I want that to be less than or equal to n over 2n minus 1. What's the other way to show something's non-increasing or to show something's decreasing besides an inequality?
Graph it.
Derivative.
Derivative.
First derivative test.
Slope.
If the slope is negative, it's decreasing. Yeah, so you could use the first derivative test to satisfy the second condition of the alternating series theorem. It's a mouthful. Okay, what do we got here? Do you think this is decreasing or not? Or not increasing? You think it's decreasing? That's not obvious at all to me. Both the numerator and the denominator are smaller in the second fraction. They might balance each other out. Twice as small? Dangerous use of terminology. I don't know about that.
Twice as big.
Yeah. I don't see it. I got to do the algebra here. I don't see it. I'm not lying. I don't see it. I didn't get enough sleep and I haven't had enough coffee. I'm going to cross multiply. All right, if I cross multiply, I'm going to get n plus 1 times 2n minus 1. On the left, that's supposed to be less than or equal to, what was it, n times 2n plus 1? Yeah. Sorry, I'm not that smart today, Jeff. I am not. I'm going to do it out. Too bad. So if I multiply that out, that's 2n squared plus n minus 1. That's supposed to be less than or equal to 2n squared plus n. Oh, that's nice. If I do a little subtraction here, these guys subtract out.
Oh my goodness.
And I get negative 1 is less than or equal to 0, which is true most days of the week. Huh? It's less than or equal to. I mean, it's the or that's the key, right? Okay, so this is true. Since it actually isn't equal to, then what we can say is that this thing is not only non-increasing, it is decreasing. True. Decreasing. For all n greater than 0. Oh, shit, that's not true. It's greater than 1, right? Yeah. If I plug in n equals 0, I'll get a negative 1, and if I crisscross a negative 1, that flip-flops the inequality. So I got to say n equals 1, which is okay. It's probably greater than or equal to 1, but do the first couple terms matter? No, it's the infinitely many suckers that are trouble. Okay, so we're good. Step 3, now that we finally proved the obvious, and that was pretty obvious. I mean, it only took us a half a page.
I thought you said you couldn't pay for that.
I did, right there.
No, I mean in your head.
I couldn't.
You said it was pretty obvious right there.
Obvious doesn't mean you can do it in your head. Obvious means you can get it done in a short amount of time. Short amount of time being like an hour or two. Anyway, next test. What's the limit as n increases of n over 2n minus 1? Focus. Okay, what do we want it to be?
0, which is not so divergent.
It's not 0, so finally we can say, oh, damn it, it's divergent. It diverges. So both endpoints diverge. All right. So our power series a fair amount of work? Yeah, you got to use the ratio test, and you got to test the endpoints. Now I can state my final conclusion. We have absolute convergence for this sum as n equals 1 to infinity. I think I got it down now. If x is in the interval from -2 to 2, excluding the endpoints, is what we just proved.
So if it would have been convergent at one of the endpoints, then it would have been like 4. We would have just written.
Yeah, so then we put out a square bracket on one side. Yeah, so if it happened to be, often like the alternating thing will give you convergence, but this time it didn't. Yeah, so if it converged on one side but not on the other, our error inequality might look like that.
Yeah, what
No,
does the E thing?
that means is an element of.
Oh, thanks. Yeah.
It does look a little like an epsilon in my handwriting, or it's in the sets. And again, ignore this sucker right there. That was just a question. So we could have convergence on one side and divergence on the other. You could have convergence on both sides. And the problems we've done so far, it's divergence on each side. All right, let's do one more. There's lots of things you can do to attack these. So you could do you can just make shit up and see what happens. You can take existing series and you can do substitutions to tweak them. But you can also, if you have a convergent series, you can integrate and differentiate them. Okay, so I'm going to take you on a little ride here. We're going to take the series that we came up with. It was like, I think, the third power series we did. It's the sum as n equals, let's see, what did I start with? I think I started with 0 to infinity of negative 1 to the n times x to the n. And we found that that was equal to 1 over 1 plus x by using a little substitution. Okay. So what I'm going to do next is I'm going to do another substitution. I'm going to substitute x minus 1 for x. So I'm going to get a new series. My series is going to be the sum as n goes from 0 to infinity of negative 1 to the n. And instead of an x, I have an x minus 1 to the n. Just because.
Why would a person desire to ever do this? Like, what?
Anybody ever take chemistry?
Yeah.
Why would anyone ever desire to mix a few chemicals together and see what happens? Hey, maybe we'll make a medicine or a bomb. What the hell? Fun stuff. Or meth, right? Right. It's all in the spirit of experimentation.
And money.
All right. So on the other side, if I do that substitution, I get 1 plus parentheses x minus 1. Okay. Can we clean up the right side of this? What does that become? 1 over x. Hey, that's a cool function, 1 over x. Okay.
No.
That was not random. I did it on purpose because I wanted to get 1 over x there. Because I wanted to talk about the natural log. Excellent, Courtney. You guys are so perceptive. Yeah. So now remember, this red one up here had an interval of convergence of that right there. So now I have a new interval of convergence because I replaced x with x minus 1. So that means I have x minus 1 is less than 1. What's the interpretation of that? Well, before it was distance from 0. Now this is the distance between x and 1. Because doesn't subtracting find you the distance between two numbers? This says the distance between x and 1 has to be less than 1. So if I transfer that onto a map, here's this one right there. This one is my radius. So this is my interval of convergence at the moment. Now, when you tweak these things, sometimes you change the behavior at the endpoints. Take my word, it's not going to change today. Not today. You can test them later if you want. So I've just created the new power series for the function 1 over x. Okay. So I'm going to write down what I think I've figured out. I think that the function 1 over x is equal to, coming back here, if I plug in a 0 for the power, what happens to everything? It goes to 1. Yeah. So I'm going to get 1 plus, what happens if I, oops, wrong button. What happens if I plug in a 1 for my n's? If I plug in a 1 for n, yeah, so if I plug in for n, I'll get negative 1 times x minus 1. So let's change that sign. Negative x minus 1. Guess what's going to happen next? I'm going to get plus x minus 1 squared. Then I'm going to get minus x minus 1 cubed, yada, 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 all the way down the line. Guess what we're going to do with this next? Give me just a couple minutes. Sorry. This is so fun. Isn't it kind of fun? We're going to integrate on both sides. Yeah, both sides. It turns out that if you have a power series that converges on an interval, then within that interval, you're safe to integrate both sides, the infinite part, forever and ever, term by term. Isn't that awesome? Okay, so we're going to integrate both sides with respect to x. All right, so what's the integral of 1 over x? Natural log of, actually it's not natural log of the absolute value, right?
Yeah.
Okay. Now technically we have a plus c going on there. On the other side, integral of 1 is, that's the derivative, it is x, yeah, it's x. And I'm going to get minus the integral of x minus 1. I will have a plus c there too, yeah. Yeah. And so maybe I'll call this one C1 and that one C2 for now. Okay. It is x minus 1 squared divided by 2. Right? Raise the power, divide by it. Remember the power rule for integration? Okay. So I'm going to have a minus x minus 1 cubed over 3. You see a pattern developing here? Right, so I could do the next one. It's going to be a plus x minus 1 to the 4th over 4, yada, 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 way down the line. I could say I'm going to have a negative 1. Oh, fine. Where? Oh, shit, I do, huh? I mean, shoot. All right. So positive, negative, positive, negative. Okay, thank you. Oh, the details, the details. They do matter. Yeah, okay. All right, so this was the first term, second term, third term, so on the line. So I'm going to put an n there. But then the powers rose each time, right? So then I believe what I'm going to have is an x minus 1 to the n plus 1 over n plus 1. Double check. Let's pick n equal to 3 and see if this formula matches what I see above. So if n equals 3, oh, it didn't work, did it? Oh yeah, maybe, oh, n equals 3 would give me this one, yeah. So if n equals 3, I get negative 1 cubed, which is negative 1. And then I get n plus 1 is 4, 3 plus 1, and 3 plus 1. Okay, that works. So the question was whether this is an n or an n plus 1 right there also. Do I have my signs right? And if you didn't correct my alternating sign, then I would have had it wrong. So thank you. Then the next question is, well, what is C? Well, we pick an easy number for x to help figure it out. Now here's the deal. These are both constants, so I could bring them to the same side. So if I did that on the left, I would have C1 minus some C2. Well, if C1 is a constant and C2 is a constant, don't those subtract to give a new constant? So let's just call it C. I'm doing constant magic. Whenever you do an integration, if you don't have bounds, you have a constant of integration you got to tack on there. So it turns out we have a constant on each side, but it also turns out it's sufficient to just put it on one side or the other. Okay, because my new constant is C1 minus C2. It's some number. Why not just call it C? Okay. All right. So then I just pick a convenient number for x to make stuff go away. Does anybody remember what the center of this interval is?
Isn't it like...
Yeah, it's 1. So the center is a good number to plug in. It is a safe number to work with. So what happens if I plug in 1? Oops, wrong button. If I plug in x equals 1 everywhere, then what I'm going to get is on the left side, ln of 1 is 0, so I just have 0 plus c. What do I get on the other side? I get x is 1, but then every one of these other infinitely many guys goes away. So it tells me the constant is 1. Okay. Okay, sorry, just let me finish down here's the final result. So what we have is that the natural log of the absolute value of x added 1, constant ended up on the left, is equal to x, get my signs right, minus x minus 1 squared over 2 plus x minus 1 cubed over 3, and so on. One last tweak. I'm going to take this 1 to the other side. How do I do it? Subtract 1. So that makes this an x minus 1 also. So now I have x minus 1 minus x minus 1 squared. Oops. So it looks a little more consistent. Oops, that's a minus there. No, that's going to leave it like that. That's what's called a power series for the natural log of x. Kind of cool. Tomorrow, which is the next time we meet, we'll do a power series for its inverse, e to the x. Yeah, tomorrow's always next time we meet, right? Thursday. Yeah. Okay, so for what x values is this true? Earlier, we were messing around, and we found this was our interval right here. So if x is bigger than 0 but less than 2. Now we can't plug in 0 because the natural log doesn't exist there. And if we tried to plug in 2, I think we'd find it diverges there also. We'd have to check that. Okay. So for now, we have a center of 1 and a radius of 1 is all we know. Okay. All right. So these problems use everything we've learned so far in Calculus 1, 2, and 3. And I think they're fun. And it reviewed sections 1 through 6. So, Zach, I hope you take your test soon. I haven't received it yet. You took yours. Yours is at the testing center?